kinematics, we study the motion of bodies without considering the forces that cause the motion. Let us first understand what is meant by the position of a body. The position of a body in space is denoted by three coordinates: x, y, and z. The path length and displacement of a body depend on how its position changes with time. To specify the position of a body, we use a reference point with respect to a set of axes. The set of axes consists of three mutually perpendicular lines labeled as the x, y, and z axis. The point of intersection of these three axes is called the origin. The origin is used as the reference point for the body. To specify the position of a body, its x, y, and z coordinates are given with respect to this rectangular coordinate system. A stopwatch is included to complete the frame of reference. When any one or more of the coordinates change with time, the body is said to be in motion with respect to the frame of reference. The motion of a body with respect to the frame of reference could be parallel to the x-axis, parallel to the y-axis, parallel to the z-axis, in the xy plane, in the xz plane, in the zy plane, or in space. When the coordinates don't change with time, the body is said to be at rest with respect to the frame of reference. Rest and motion are relative terms and are always specified with respect to the frame of reference. A simple example of a car moving on a straight road will make this concept clear. Suppose you take a frame of reference with a fixed point on the road as the origin. We say that the car is moving. However, when you take a person sitting in the car as the origin of the frame of reference, then the driver of the car is at rest, as, in this case, the frame of reference itself is moving along with the car. If the body has one-dimensional motion, then we consider only one axis of reference. It is either the x-axis or the y-axis. This type of motion in a straight line is known as rectilinear motion. If the body is moving in a plane, then we consider any two of the three reference axes. If the body is moving in space, which is three-dimensional, then we have to consider all the three reference axes. Let us examine rectilinear motion more closely. To study the motion of a body along a straight line, we have to align the straight line along one of the axes, which is usually either the x-axis or the y-axis, and then choose a convenient origin, O. Positions to the right of O are taken as positive, and to the left of O as negative. Positions above O are taken as positive, and below O as negative. With time, the position of the body changes and describes a path. Let's consider the example of a man walking along a straight line. Take the x-axis to coincide with the straight line. Fix the origin of the axis at the point from where the man starts walking. This is represented by x is equal to 0 when time t is equal to 0. A and B represent the position of the man at different instances of time. In the first instance, the man moves from O to A. The distance moved by him is OA, which is 36 meters. This distance is the path length traversed by the man. In the second instance, the man moves from O to A and then moves back from A to B. The distance between points A and B is 12 meters. Now, the path length traversed by the man is OA plus AB equal to 36 meter plus 12 meter is equal to 48 meter. The path length is a scalar quantity as it has only magnitude and no direction. Path length is the distance traversed by a body, whereas displacement is the change in the position of the body. Let us consider an example to understand displacement better. Let an object be placed at point O, which is the origin. Let x1 and x2 be the positions of an object at time t1 and t2. Its displacement delta x in time delta t is equal to t2 minus t1 is given by the difference between the final and initial positions. Delta x is equal to x2 minus x1. When x2 is greater than x1, delta x is positive. And when x2 is less than x1, delta x is negative. A positive sign indicates displacement to the right side. A negative sign indicates displacement to the left side. Since displacement has magnitude and direction, it is a vector. For example, let's consider the displacement of the man moving from O to A. Distance delta x is the difference between the initial point and the final point, which is equal to 36 meters. The displacement of the man in moving from A to B is delta x, where delta x is the difference between 24 meters and 36 meters, which is equal to minus 12 meters. The magnitude of displacement and the path length traversed by an object may or may not be the same. For the motion of the man from O to A, the path length is 36 meter, and the magnitude of the displacement is also 36 meter. For the motion of the man from O to A and back to B, the path length is 48 meter, whereas the magnitude of the displacement is 24 meter. There may be cases where the displacement of an object may be zero, even though it has moved, but its path length will not be zero. For example, the man starts from O, goes to A, and comes back to O. The final and initial position of the man being the same, his displacement is zero. However, the path length of his journey is 72 meters. Let us observe some types of motion and the corresponding graphical representation. Case 1. When an object is stationary, its position does not change with time. A car is stationary, say, at a point 40 meters from the origin. The graph will be a horizontal line passing through the 40-meter mark on the y-axis. Case 2. If the car starts at point 0 and covers equal distances in equal intervals of time along a straight line, the graph will be an inclined line. When a body covers equal distances in equal intervals of time along a straight line, it is said to be in uniform motion. Case 3. If the car starts from the position of rest, picks up speed, and moves with uniform speed for some time, later, the brakes are applied and its speed gradually decreases, and the car finally comes to rest, this graphical representation shows all the three types of motion, that is, acceleration, uniform motion, retardation, and back to rest. Are the words velocity and speed synonymous? Yes, they are in our day-to-day language. However, in science, they are not. Speed is a scalar, whereas velocity is a vector. Speed has only magnitude, whereas velocity has magnitude as well as direction. Speed depends on the magnitude of the path length described by a body and the time taken to describe this path. Velocity, on the other hand, depends on the displacement of a body and the time taken for this displacement. Let's start with average velocity. A body moving in a straight line is said to be in a rectilinear motion. Let's plot an xt graph of this motion. A body starts at the origin and travels through a certain distance x meters in time t seconds. Let us mark 2 points A and B on the graph obtained. Let us study the motion of the body from point A to point B in detail. x1 and x2 are the positions of the body at time t1 and t2 respectively. The displacement delta x is the difference between x2 and x1. The time interval delta t is the difference between t2 and t1. The average velocity is the ratio of the change in position or displacement delta x and the time interval delta t in which the displacement occurs. The SI unit for velocity is meter per second. The velocity of vehicles is generally expressed in kilometers per hour. Let us take the readings from the graph and calculate the average velocity of the body from point A to point B. Delta x is equal to x2 minus x1 is equal to 42 minus 10 is equal to 32 meters. Delta t is equal to t2 minus t1 is equal to 7 minus 3 is equal to 4 seconds. V bar is equal to 32 by 4, which is equal to 8 meters per second. V bar represents the slope of the line joining points A and B. Slope is equal to tan theta is equal to x2 minus x1 by t2 minus t1. If you observe the graph carefully, you will find that the displacement is different in different intervals of time. That is, from the 3rd to the 4th second, from the 4th to the 5th second, and so on. For calculating the average velocity, we take the total displacement and total time elapsed. In other words, it is the average of different velocities obtained at different instants of time. For example, When a car is traveling on a straight road, the velocities at various instances of time, say t1, t2 and t3, are taken as v1, v2 and v3 respectively. Then the average velocity is the average of the three velocities recorded. Let us consider a scenario where a person is traveling from his home to his workplace and back home in his car. The path traversed by him is a straight line. When he goes to work, the displacement of the car is equal in equal intervals of time. Here, the displacement is considered to be in the positive direction. The xt graph, when plotted for this motion, is a straight line passing through the origin and making a positive acute angle theta with the time axis. The car is in a state of rest or at the same position for some time as long as the man is at his workplace. For that time span, we get a straight line parallel to the time axis when plotted on the graph. When the man returns home, the car makes equal displacements in equal intervals of time, in the negative direction. The graph now is a straight line, making a negative slope with the time axis. When the total displacement of the car is considered, it is 0. We know that speed depends on the magnitude of the path length described by a body and the time taken to describe this path. Average speed is the ratio of the total path length and the total time taken for the motion. The unit for average speed is the same as that for average velocity. That is, meters per second or kilometers per hour. When a body moves in a straight line in the same direction throughout its motion, the magnitude of the displacement is equal to the total path length. In such a case, the magnitude of the average velocity is equal to the average speed. Joe travels by a car from his residence to his office, which is 15 kilometers away on a straight road, in 1 hour. We can say that the average velocity of the car is 15 kilometers per hour. Does the speedometer of the car show a reading of 15 kilometers per hour throughout the journey? No. The speedometer reading was fluctuating continuously between 0 kilometers per hour at signals, 5 kilometers per hour at traffic jams, and 60 kilometers per hour on the freeway. When a body moves in a straight line, the magnitude of its velocity is equal to its speed. The speedometer reading gives the instantaneous velocity at that particular moment. What is instantaneous velocity? The velocity at an instant or instantaneous velocity is defined as the limit of the average velocity as the time interval, delta t, becomes infinitesimally small. In differential calculus, the right-hand side of this equation is called the derivative of x with respect to t. It represents the rate of change of position with respect to time at that instant of time. We can obtain the value of instantaneous velocity either from the xt graph or numerically using differential calculus if the relation between x and t is known for the motion. Let's understand how to calculate instantaneous velocity using an xt graph. We first mark a point P on the graph at which the instantaneous velocity of the body has to be found. We mark 2 points P1 and P2 on either side of P. Join points P1 and P2. Find delta t and delta x. When delta t is reduced, we get lines Q1, Q2, etc. On further decreasing the value of delta t, we finally get one line, which is the tangent to the curve at point P. The slope of this tangent represents the instantaneous velocity at point P. Slope is represented by tan theta as shown in the graph. This graphical method of finding the instantaneous velocity at any point is cumbersome. Therefore, we generally use the numerical method using calculus for finding the instantaneous velocity at any point. Let's solve a problem using this numerical method. The position of a particle that moves along a straight line is defined by the relation x is equal to t cube minus 6t square minus 15t plus 40, where x is expressed in meters and t in seconds. What is the instantaneous velocity at t is equal to 0 second and t is equal to 2 seconds? What is the average velocity between t is equal to 2 seconds and t is equal to 4 seconds? Solution: the equations of motion are x is equal to t cube minus 6t square minus 15t plus 40. V is equal to dx by dt is equal to 3t square minus 12t minus 15. Label these equations 1 and 2. At t is equal to 0 seconds, we need to find the value of v. Substituting t is equal to 0 in equation 2, v is equal to minus 15 meters per second. The particle here is moving towards the left. At t is equal to 2 seconds, we need to find the value of v. Substituting t is equal to 2 in equation 2, v is equal to 3 multiplied by 2 square minus 12 multiplied by 2 minus 15. 12 minus 24 minus 15. Minus 27 meters per second. The particle here is moving towards the left. Average velocity is equal to x4 minus x2 by 4 minus 2. To find x4, we need to substitute t is equal to 4 in equation 1. x4 is equal to 4 cube minus 6 multiplied by 4 square minus 15 multiplied by 4 plus 40 is equal to minus 52 meters. The particle is situated to the left side of the origin. Similarly, to find x2, we need to substitute t is equal to 2 in equation 1. x2 is equal to 2 cube minus 6 multiplied by 2 square minus 15 multiplied by 2 plus 40 is equal to minus 6 meters. The particle is situated to the left side of the origin. Average velocity is equal to x4 minus x2 by 2. Minus 52 minus of minus 6 by 2 is equal to minus 46 by 2, which is equal to minus 23 meters per second. Therefore, the average velocity between t is equal to 2 seconds and t is equal to 4 seconds is minus 23 meters per second. When you observe the motion of an electric train, you find the train picks up high speed even before leaving the platform. The train travels at constant high speed until it approaches the next station. There is a sudden drop in speed when it enters the station till it finally stops. The first and the last part of this train's motion has high positive acceleration and very high negative acceleration or retardation. Acceleration of a body is the rate of change of its velocity with time. The average acceleration A dash is defined as the change of velocity divided by time. V2 and V1 are instantaneous velocities at times t2 and t1. The SI unit of acceleration is meter per second square. On the VT graph, the average acceleration is represented by the slope of the line joining the points V1, T1 and V2, T2. Just as we defined instantaneous velocity, we can similarly define instantaneous acceleration. On the VT graph, instantaneous acceleration at any point on the curve is represented by the slope of the tangent drawn at that point. Like velocity, acceleration is also a vector with both magnitude and direction. The acceleration of a body can change with either a change in the magnitude of its velocity or change in the direction of its velocity, or both. In rectilinear motion, we have only two directions of motion, positive and negative. Therefore, we have two types of velocities, positive and negative. Similarly, we have two types of acceleration, positive and negative. Formulating a proper and consistent sign convention for acceleration is very important. Let's understand what constitutes positive and negative acceleration. Zero acceleration stands for uniform velocity. That is, the velocity does not change with time. Let us consider cases where acceleration is positive. Case 1. Let us consider a body, say, a car moving along a straight line. That is, from point A to B, with increasing magnitude of velocity. The body is said to be moving in the positive direction. Here, delta V is positive and direction of motion is positive. Therefore, with these two values being positive, acceleration is also positive. Case 2. In this case, the car is moving in a negative direction. That is, from point B to A, with a decrease in the magnitude of velocity. Here, delta V is negative and the direction of motion is also negative. Since the product of two negative values is positive, acceleration in this case is also positive. Let us now consider cases where acceleration is negative. Case 1. Now consider the car moving in a positive direction. That is, from A to B, with a decrease in the magnitude of velocity. Here, delta V is negative and direction of motion is positive. Since the product of a negative and a positive value is negative, the acceleration in this case is negative. Case 2. In this case, the car is moving in a negative direction. That is, from B to A, with an increase in the magnitude of velocity. Here, delta V is positive and direction of motion is negative. Since the product of a positive and a negative value is negative, the acceleration in this case is also negative. To decide whether acceleration is positive or negative, the terms retardation or deceleration are confusing while solving problems. Here is an easy way to get the sign convention for acceleration right. In the 4 cases we have just studied with respect to points A and B between which the body traverses, let us fix the velocities of the body at these points as v at A and v dash at B. The 4 cases are tabulated. If the origin and direction of motion are discarded, we are left with the type of acceleration and the relation between the velocities at 2 points. If v and v dash are taken as the initial and final velocities in any given problem, then if v is less than v dash, then acceleration is positive, else negative. Let us see what the xt graphs for positive, negative and zero acceleration look like. The xt graph for motion with positive acceleration curves upward. For negative acceleration, it curves downward. For zero acceleration, it is an inclined line. Let us see what the Vt graphs for all 4 cases explained earlier look like. Body with positive acceleration, that is, positive direction and positive velocity. The graph is an inclined line above the x-axis with upward inclination. Body with positive acceleration, that is, negative direction and negative velocity. The graph is an inclined line below the x-axis with upward inclination. Body with negative acceleration, that is, positive direction and negative velocity. The graph is an inclined line above the x-axis with downward inclination. Body with negative acceleration, that is, negative direction and positive velocity. The graph is an inclined line below the x-axis with downward inclination. Displacement x, velocity v, acceleration a, and time t are related. Let's derive how each term is related to the other. Before deriving the kinematic equations, we have to learn about a, t, and vt graphs. You know that acceleration can change with time and the position of the body. Here, we will deal with bodies moving with constant acceleration. Vt graphs help us understand the given problems a little more clearly and solve them easily. Let us look at one interesting aspect of the Vt graph. This graph actually helps find the displacement of a body. Let us consider an example where a body is moving with a constant velocity, v, during the time interval, t, where t is equal to t0 is equal to 0 to t is equal to t1. Let us draw the Vt graph representing this motion of the body. We get a line parallel to the x-axis. We know that velocity of a body is the ratio of its displacement and the time interval. We can say that displacement is a product of velocity and the time interval. This is the product of velocity v and time interval t1. This is nothing but the product of the height and the length of the rectangle formed when a line is dropped perpendicular to the x-axis. That is, the area of the rectangle. The area under the line up to the x-axis indicates the displacement of the body. The same concept applies to bodies moving with a constant acceleration. In this case, the Vt graph will be an inclined line, and the area under this inclined line up to the x-axis represents the displacement. There are three important kinematic equations for uniformly accelerated motion. Let us derive these equations one at a time. The first equation is the relation between initial velocity, v naught, final velocity, v, uniform acceleration, a, and time t. The velocity of an object is v naught at t naught is equal to 0 and v at time t. Average acceleration, a dash, is the ratio of the difference between v and v naught and the difference between t and 0. The value of a dash is equal to acceleration when acceleration is constant. By cross-multiplying and rearranging, we get the value of velocity as the sum of v naught and the product of a and t. This is equation 1 of motion. The second equation represents the relation between displacement x, initial velocity v naught, acceleration a, and time t. The area under the line PQ up to the x-axis represents displacement x. Displacement x is represented by the area between the lines joining points O, P, Q, and S. This is equal to the sum of the areas formed by the triangle PQR and the rectangle PRSO. We get the value of x as half the product of t, and the difference of v and v naught plus the product of v naught and t. From equation 1, the value of v is the sum of v naught and the product of a and t. Here, the value of the product of a and t can be derived as the difference between v and v naught. Now, replacing the v minus v naught in the equation by a t, we get x is equal to v naught into t plus half at square. This is equation 2 of motion. The third equation is the relation between initial velocity v naught, final velocity v, acceleration a, and displacement x. The average velocity of a body v dash is half the sum of v and v naught, where acceleration is constant. We know that displacement is the product of average velocity and time, that is, the product of v dash and t. From equation 1, v is the sum of v naught and at. By rearranging the equation, we get time t equal to the ratio of the difference of v and v naught and a. Substituting the values of t and v dash in the equation for displacement, we get x equal to the ratio of the difference between v square and v naught square, and twice the value of a. By rearranging the above equation, v square is equal to v naught square plus 2ax. This is equation 3 of motion. Let's now use calculus to derive the equations of motion that were derived so far using basic mathematics. The new set of equations we shall derive is very useful in solving complicated problems. Let's start with uniform rectilinear motion. Observe the xt graph. T0 is not equal to 0, and x0 is also not equal to 0. dx by dt is equal to v, which is a constant. Initial values are x naught, t naught. Final values are x, t. Cross-multiplying equation 1, we get dx is equal to v into dt. Integrating both sides, we get integral x naught to x dx equal to v into integral t naught to t dt. We get x minus x naught is equal to v into t minus t naught. On transposing, we get x equal to x naught plus v into t minus t naught. This equation is used to obtain the position coordinate x of the body at any time t. This equation can be used when the values of x naught and t naught are both or either of them is equal to 0. In other words, the equation is applicable under all conditions. Now let's derive equations for uniformly accelerated rectilinear motion. In this type of motion, the acceleration of the particle is a constant dv by dt is equal to a, which is a constant. The initial values are x naught, t naught and v naught. Similarly, the final values are x, t and v. dv by dt is equal to a. By cross-multiplying, we get dv equal to a into dt. Integrating both sides, integral v naught to v dv is equal to a into integral t naught to t dt. v minus v naught is equal to a into t minus t naught. Rearranging the equation, v equals to v naught plus a into t minus t naught. This is equation 1 of motion. We know that dx by dt is equal to v. Substituting this value in equation 1, we get dx by dt is equal to v naught plus a into t minus t naught. By cross-multiplying, we get dx is equal to v naught plus a into t minus t naught multiplied by dt. Integrating both sides, we get x minus x naught equal to v naught into t minus t naught plus half a into t minus t naught whole square. This is equation 2 of motion. v is equal to dx by dt and a is equal to dv by dt. From equation 1, dt is equal to dx by v. Substituting the value of dt in equation 2, we get a equal to v into dv by dx. We know that this value of a is a constant. By cross-multiplying, we get v into dv is equal to a into dx. Integrating both sides, we get integral v naught to v. v into dv is equal to a into integral x naught to x dx. This is equal to half v square minus v naught square equals to a into x minus x naught. Rearranging the equation, v square is equal to v naught square plus 2 a into x minus x naught. This is equation 3 of motion. We know what displacement is. Now, let's understand what relative displacement between two bodies in rectilinear motion is. When several bodies move independently along the same line, time should be recorded from the same initial instant for all bodies. And displacements measured from the same origin and in the same direction. This implies that a single clock and a single measuring tape should be used. Let's consider two bodies, A and B, moving along the same straight line. At an instant, their position coordinates are x, A and x, B respectively. This implies that A is at a distance x, A with respect to origin O, and B is at a distance x, B with respect to the same origin O. This implies that the distance is measured with respect to the fixed point O, which is the origin. X, B minus x, A is the relative position coordinate of B with respect to A and is denoted by xB by A. When both A and B are moving, we take the distance at a particular instant. Differentiating relative distance xB by A with respect to time, we get relative velocity, which is denoted by VB by A. By differentiating, we get VB by A is equal to VB minus VA. Coming to the sign convention, regardless of the position of the origin O, with respect to the positions of A and B, a positive sign for xB by A means that B is to the right of A, and a negative sign means that B is to the left of A. A positive sign of VB by A means that when B is observed from A, the motion of B is in the positive direction, that is, rightward direction. A negative sign of VB by A means that when B is observed from A, the motion of B is in the negative direction, that is, leftward direction. This concept can be applied to determine the relative distance and relative velocity. Let us consider a few cases where two cars are traveling on a straight road with varying velocities. Case 1. Cars A and B are moving on a straight road with equal uniform velocity of 10 meters per second. At the time of initial observation, that is, when TB0 is equal to 0, B is 40 meters behind the crossroads, and A is 20 meters in front of the crossroads. What is xB by A and xa by B at time t0 equal to 0? Taking the crossroads as the origin O and time equal to 0, xB by A is equal to xB minus xa. This is equal to minus 60 meters. Minus sign indicates that the car B is on the left side with respect to A. xa by B is equal to xa minus xB. This is equal to plus 60 meters. Plus sign indicates that the car A is on the right side with respect to B. 2. What is xB by A and xa by B at time t equal to 5 seconds? Here, VA is equal to 10 meters per second. X, A, O is equal to plus 20 meters. T, A, O is 0 second and TA is equal to 5 seconds. we need to find XA. XA is equal to XAO plus VA into TA minus TAO. On substituting and simplifying, we get XA equal to plus 70 meter. Calculating for XB, here VB is equal to 10 meters per second. XBO is equal to minus 40 meter. TBO is 0 second and TB is equal to 5 second. XB is equal to XBO plus VB into TB minus TBO. On substituting and simplifying, we get XB equal to plus 10 meter. Now, calculating for XB by A, which is equal to XB minus XA. On substituting values and simplifying, we get XB by A equal to minus 60 meter. And calculating for XA by B, which is equal to XA minus XB. On substituting values and simplifying, we get XA by B equal to plus 60 meter. We observed that XB by A and XA by B are same in magnitude. This implies that the distance between the two cars remains constant irrespective of time elapsed from the first observation. What is the relative velocity of B with respect to A at time t equal to 4 seconds? We know that the values of t, VA and VB are equal to 4 seconds, plus 10 meter per second and plus 10 meter per second respectively. As the two cars are moving with uniform velocity, VB by A is equal to VB minus VA. By substituting and simplifying, we get 0 meter per second. When and where the two cars come side by side? By comparing the results of the first and the second bits of case 1, we can say that the cars never come side by side. Case 2. The position of the cars at initial observation being same as in case 1. Now, car A has uniform velocity of 10 meters per second, and car B has uniform velocity of 20 meters per second. 1. What is VB by A and VA by B at time t equal to 4 seconds? As A and B are moving with different uniform velocities, the values of t, VA and VB are 4 seconds, 10 meter per second and 20 meter per second respectively. Here, VB by A is equal to VB minus VA. On substituting and simplifying, we get VB by A equal to plus 10 meter per second. Calculating the value of VA by B, it is equal to VA minus VB. On substituting and simplifying, we get VA by B equal to minus 10 meter per second. 2. When and where the two cars come side by side? When the cars A and B come side by side, their position coordinates with respect to the origin must be the same. That is, XA is equal to XB. This can be called equation 1. Here, XA is equal to XAO plus VA into T minus T naught. By substituting and simplifying, we get XA equal to 20 plus 10T. This is equation 2. Similarly, XB is equal to XBO plus VB into T minus T naught. By substituting and simplifying, we get XB equal to minus 40 plus 20T. This is equation 3. Substituting equations 2 and 3 in equation 1. On further simplifying, we get T equal to 6 seconds. This is equation 4. Further substituting equation 4 in equation 2, we get XA equal to 80 meter. The two cars A and B come side by side at 6 seconds when their position coordinate is 80 meters. Case 3. At the time of initial observation, that is, when T naught equals to 0, car A is 40 meters behind the crossroads, and car B is 90 meters ahead of the crossroads. Car A is moving towards right with a uniform velocity of 10 meters per second. Car B is moving towards left with a uniform velocity of 15 meters per second. 1. What is VB by A and VA by B at time t equal to 3 seconds? VB by A is equal to VB minus VA. By substituting and simplifying, we get VB by A equal to minus 25 meter per second. Similarly, VA by B is equal to VA minus VB. By substituting and simplifying, we get VA by B equal to plus 25 meter per second. When and where the two cars cross each other? When the two cars cross each other, their position coordinate is the same. That is, XA is equal to XB, which is equation 1. Here, XA is equal to XAO plus VA into T minus T naught. By substituting and simplifying, we get XA equal to minus 40 plus 10T, which is equation 2. Similarly, XB is equal to XBO plus VB into T minus T naught. By substituting and simplifying, we get XB equal to 90 minus 15T, which is equation 3. Substituting equations 2 and 3 in 1, we get T equals to 5.2 seconds, which is equation 4. Substituting equation 4 in 2, we get XA equal to 12 meter. Therefore, the two cars cross each other at 5.2 seconds when the position coordinate is 12 meters.